welcome everyone. Hello, I am here with a new chapter, and today's topic of discussion is center of mass. So, before starting the concept of center of mass, let's start with the center of gravity. What do you know about the center of gravity? That is very much important to understand the concept of center of mass. Okay, so let's start with a diffused body. That means it is not a point mass that has some amount of that has a volume. Okay, so we can consider this diffuse system, this diffused body or distributed body can be considered as a accumulation of infinite number of point masses that I have shown here. These dots are the point masses. Okay, now each and individual point mass is attracted by the earth. Okay, so let this point mass has the mass m1 and this one has mass m2, this one got the mass m3. So that means force on this point mass due to earth is m1g, that is the weight of the point mass, and force on this point mass, that is m2, that has the force on it is m2g due to the gravity, and on this point mass that has the mass m3, force on it is due to gravity is m3g, and like that we can find the force due to gravity on each and every point masses. Okay, and these all forces are acting in the downward direction. This is the, as we know, for the case of gravity, it always acts towards the center of the earth. So all these forces are acting in the downward direction. Now problem is that if you have infinite number of forces, that means if you have infinite number of vectors, so that is really a problem to make any kind of calculation with infinite number of vectors. So what we do, actually we actually do a little bit of trick. That thing is, we consider this amount of force, that means this total force on this whole object is actually m1g plus m2g plus m3g and so on. So this whole amount of force actually acts from a point. Okay, so that is our consideration. That is not the real case. Actually the gravitational pull is acted on each and every individual point masses, each and every corner of the body feels some some amount of attraction force due to the earth. But we assume that this, if you want to go with this number of vectors, that actually the number may go to the infinity. That means it can go to the up to 10 to the 30 or 40. Okay, so just keep them aside and just take a consideration that this force, that means this m1 plus m2g plus m3g, this complete force is going to act from a point, that is maybe this point. Okay, so we have considered the total force due to the gravitation is acting from this point. So this point is called actually the center of gravity. Okay, and the amount of force will be, take the g common, m1 plus m2 plus m3, and that will be this m1 plus m2 plus m3, this is actually the mass of the whole body, and it is capital mg. Now idea is that this, that means your object is pulled from that point. Now if you want to hold that object on your fingertip, then you have to put upward force at that point only. You don't need to put a force here or here. You have to just, because there is just our consideration is that we just, this forces is replaced by this single force. Okay, so that means there is no this m1g, m2g, m3g or rest of the terms. So that is only single force is acting, that is capital M into G, and it is acting from this point and acting obviously in the downward direction. Now if you want to, okay, if you leave it with this force, then this object will move in that direction due to this force of attraction. But if you want to hold this object on your fingertip, then you have to put your finger here and apply, and you have to apply a force in upward direction, so that your upward applied force and the total downward force can cancel each other, so that this object doesn't have any kind of motion. So that is called balancing, that actually we do when we want to balance something on our fingertip. Okay, so that is all about these things. Is only we have only considered the force of gravitation, but there are lots more forces there, like there may be some kind of electromagnetic force, maybe, okay, electromagnetic field is a compound thing. Let separate these two things. Let there is some kind of charge on this, there's some kind of charge on this object, and there is a electric field. Okay, so that means this charge will feel some amount of force due to the electric field. So for that case, we can again adapt this kind of concept, because each and individual point of this object will get some kind of attraction force, or say get some kind of repulsive force due to the electric field. And instead of using this all force components that has the number of very large number of forces, so just take a assumption, the force is resultant force of these individual forces, that means F1, F2, F3, some of these all forces, the resultant force is being acted from a particular point, and similar concept we used here. So we can use the similar type of concept there also, and we can find the point where we should apply a force to make the object static. Now similar thing can be considered for the case of friction. Friction is also it actually acts at the interface, okay, where the object and a plane is touched. So there maybe this one is the object and it is the plane, so that means this object is touched here, this region, with the surface below it, so that means the friction is acting here. But if you just take a close look, you will find that this is a complete whole surface that may have this kind of shape, that is a whole surface. So friction is acting from here, from here, from here, and from here. Or actually friction acts on the surface, that means on each and every individual point on the surface actually feels some amount of frictional force. Again we just use a term, that is Fr equals to mu n. So that is, we just only consider a single force, not every individual F1, F2, F3. Okay, so we assume that the whole force is acting at some point, and if you want to move the object, if you just want to make some kind of translational motion, if you don't want to have any kind of rotational motion, you have to put your force at that point where the resultant force is being applied. Okay, so that means if you apply a force here, some amount of force, maybe it is your F external, and your weight is applying from that point, it is applied from that point. So just check that there is the distance, perpendicular distance between the two forces, and that will create some kind of rotational motion. Okay, So that means if you want to just balance your object, that means if you don't want to assure any kind of rotation in your object, you have to put your external force on that point from where the total gravitational force is being applied. Okay, and if you don't do that, your object will start to rotate. Okay, beside that, instead of you have applied this amount of force, that means you have applied the same equal amount of force, that is gravitational force, you have applied actually exactly same amount of force that is being applied by the gravitational field, that is mg. Okay, so that means your applied force is equal to the weight of the object. That means you will get actually you are getting a resultant zero translational motion. That means there is no resultant force at all on the object, because your external force and your mg is downward, external force is upward. Those two things has the same magnitude but opposite in direction, so that means resultant will be zero. So you will not going to get any kind of translational motion due to this external force, but you will obviously get a rotational motion for this, because your external force is not at the same point where the gravitational force is acting. Okay, so there is the point of action is different of these two forces, so that means that force will create a rotational motion. Okay, so main concept of balancing is there will be no rotational motion, there will be no translational motion. Okay, so that thing is called balancing. So if you just want to do that, you have to put the same amount of force, and you have to put the force at the same point where the gravitational force is being applied, where the resultant electric force is being applied, where the resultant frictional force is being applied. Okay, at that point you have to put the external force. Now if you want to simply the translational motion, you can increase your external force. That means that amount of force you are going to apply, you can increase that. If you just make this F external greater than mg, and if you just put here, now you will get a simple translational motion, not a rotational motion, because your point of action of these two forces are same. So that means these two forces can't create any rotational motion, so you will get a resultant translational motion. Okay, so from here the concept of center of mass is started. So this point is called center of gravity, from where the gravitational force is applied. And if you considered when you consider the gravitational force, you will always say about the center of gravity. But if you want to make whole things actually general, so then we look for a point, similar type of point like the center of gravity, will look similar type of point, that is called center of mass. Center of mass is a point where you when you apply some amount of force on it, that actually produces translational motion instead of producing some kind of rotational motion. That is the concept of center of mass. So concept of center of gravity is only applied for the gravitational force field. That means when the object is feeling some amount of gravitational force only, there is no other kind of force like friction or electric field, electrostatic force or magnetostatic force. So then only gravity, center of gravity, concept of center of gravity is applied. Like you know about the center of buoyancy, I think. If you don't know, you will learn that in our upcoming classes. So like that simple center of buoyancy also a point where the upthrust, when we immerse some object, when we actually take some object and put it into water or into a gas, it feels some kind of upthrust, that is called force of buoyancy. Some kind of that property is called actually buoyancy. Liquid and gas has some kind of property, and it is actually described and explained by Archimedes. Okay, so that force of buoyancy or upthrust, it actually acts on each and individual point. Okay, but we actually consider that this forces, the resultant force actually is being applied from a particular point, is called center of buoyancy. Okay, so there is a this type of concept is being this type of concept this concept is actually is being applied on the each and every kind of force fields. Okay, so to generalize that, in we already have center of gravity, center of buoyancy. Now if you want to generalize that, you want that I don't want this different whole different things, all these different points, center of gravity or like center of buoyancy. So this, to generalize that, we just take a concept of center of mass, that is the point about which the total mass of the object is equally distributed. Okay, so that is the center of mass, concept of center of mass. Concept of center of mass says that the point, it is a point about which the total mass of the object is equally distributed. Okay, so that is the center of mass. Now we are going to derive some concept, some definition, actually some definition of center of mass. So actually we are not going to get some definition of center of mass, we are just going to get some definition of center of gravity actually. And for symmetrical structure, for structure that has some kind of symmetry, like is sphere or cube or cylinder. So this kind of structure, center of gravity and center of mass are the same points. Okay, so for some irregular structure, that center of mass and center of gravity may be different slightly, but for symmetrical structure these 2 points are same. So if we can get some definition of center of gravity, we can actually use that definition for the center of mass also. Okay, so let's start with the condition of balancing. If you want to balance an object, the net anti-clockwise torque must be equal to the net clockwise torque. That means this is a bar, okay, and this is your fulcrum. Net anti-clockwise torque must be equal to the net clockwise torque, then your object, then your this bar will be, then this bar will be balanced. Now we just considered two things, just considered two mass. Okay, so here there is a one mass m1 and here is another mass m2. Okay, so if you this rule is massless, like you just these things, these problems you just you already did this kind of problems in your class 10, maybe class 10 in your okay, in class 10 maybe. So let this rule is massless, and this is the fulcrum. Here you have a mass m1 that has a weight of m1g, and here you have another mass that has the weight m2g. Okay, now this mass is placed at a distance from the fulcrum r1, and this mass is placed at a distance r2 from the fulcrum. Then that anti-clockwise, this mass will produce an anti-clockwise moment of force, and this mass will produce a clockwise moment of force. And as you know the moment of force, that is the torque, that is the force multiplied by the distance from the fulcrum. Here the force is your m1g and the distance from the fulcrum is r1. So your anti-clockwise torque will be m1g r1 and your clockwise torque will be m2g r2. These two things must be equal. Your g will cancel, that means m1 r1 equals to m2 r2. This is the concept, this is the idea. Now if you consider these things not to be massless, that means this I just consider this scale is massless, but if you don't want to consider that things, you just want to find out some kind of things that this actually rule has some kind of mass, and you have just considered this rule is actually composed of infinite number of point masses. Okay, so now this portion of the rule will create a anti-clockwise torque, and this portion of rule will create a clockwise torque. And the anti-clockwise torque, okay, now to find the anti-clockwise torque, you have to find the force on individual points. Like this is your ml1 and this point is your ml2. Why ml1? M is the mass, L is for the left side, okay, and 1 is your first point mass. So ml1 actually shows the mass of the first point on the left hand side of the rule. This is ml2, this one has the mass ml3, like, so that means it has a weight ml1g. This l1 is on the suffix ml1g, and this point has the weight of ml2g. So that means the total weight will be of the left hand side will be ml1, sorry, here I have written the torque. So that means this force will, that may just take assume that this ml1 is at a distance r1 from the fulcrum. So that means this one will have a torque ml1 r1 into g. ml1g is the force and r1 is the distance, plus the second mass has the weight of ml2g and it is at a distance r2 from the this fulcrum. So that means it is r2, and that's so on. So we will get these things ml1 r1 plus ml2 r2 plus ml3 r3 into g. On the right hand side, for the right hand side, the masses are mr1, mr2, mr3 and mr4 and so on. So that means let this mr1 has the weight of mr1g and it is at a distance of r1 prime, okay, and the second mass is your mr2 and weight will be mr2g and that is at a point r2. I know r2 prime, I know it is quite messy here, but that we don't need this definition at all. We just, sorry, we don't need that derivation of this definition. We just want to know the definition, okay. So that is the thing. So your total torque, clockwise torque will be mr1 g r1 prime, mr2 g r2 prime, okay. Now you can get this g out and this g will cancel, so that will be total. Now this is mass into distance from the axis of rotation. Again, this is mass into axis of mass multiplied by the axis of distance from the axis of rotation, okay. So anything multiplied by the distance from axis of rotation is called moment of that thing. Force into distance from the axis of rotation is the moment of force, okay. So momentum multiplied by the distance of axis of rotation is the moment of momentum, that is called angular momentum, and the moment of force is called torque. Like that, mass multiplied by the distance of rotation is called moment of mass, okay. So that is your total anti-clockwise moment of mass, your equals to clockwise moment of mass, because you just get these g's out, okay. On from the both hand side, this g's cancels actually, okay. Now, so that means if your net anti-clockwise moment of mass equals to net clockwise moment of mass, that means net moment of mass is 0 about the center of mass, okay. If you want to make an object balanced, about some particular point, then about that point the moment of mass of that object must be 0. That is the concept of center of mass. Okay, so we got the concept of center of mass. So first definition of the center of mass is that center of mass is a point about which the total mass of the body is equally distributed. The second definition of the center of mass is a point the moment of mass about which is 0. Okay, clear? So that is our total idea. Okay, and also we have a third definition, that is the center of mass in any object is a point if you consider the whole mass of the object is concentrated at that point, then moment of mass of that